Hello friends, MoNaCo here, our fifth lecture note in physical behavior of matter. We're going to cover heat during the phase change of vaporization and fusion today. And these are really going to be just pretty much about water and how it takes a lot of energy to get water to melt and boil or freeze and condense. There's a lot more energy involved in those phase transitions than there is in actually changing the temperature of a sample of water. So we're going to complete heat of fusion and heat of vaporization problems related to this. So there's two more specific equations we must master. Those are heat of fusion and heat of vaporization for water. So let's get to it. Why can't we use that QMC delta T equation to calculate the heat involved in melting or boiling a substance? Well, primarily because if we remember back to our heating and cooling curves, when a sample of matter goes through a phase change, the kinetic energy, i.e. the temperature, doesn't change. There is no change in temperature. So how can you figure out how much heat is added or removed from that sample if there's no change in temperature? Because all the calculations we've done so far involved Q equals M times C times delta T. Well, there's a more specific set of equations that cover those phase transitions. The first one is about the heat of fusion. It's the amount of heat or potential energy required to change a substance from a solid to a liquid. Table B covers it for H2O. In Table B, we had the specific heat capacity of water, which is 4.18. It also has the specific heat of fusion and specific heat of vaporization for water. Now, the heat of fusion equation is in the heat calculations along with QMC delta T, but it's actually simpler. There is no change in temperature involved. It's just Q equals M times HF. So M, again, Q is again heat in joules, M is mass in grams, and the heat HF values is like joules per gram. It's a constant, HF equals a constant, and the units are joules per gram. Now, how many joules are required to melt 225 grams of ice at 0 degrees Celsius? So if we're thinking about our heating and cooling curve, we're melting, so we're at heating curve. We're kind of like at the first flat line. We're just like, we just made it to here, and we have to figure out how much heat gets us to, like here, to the end of that line, to melt that ice. So the way we set this up, we figure out our Q and our M and maybe our HF. HF for heat of fusion. Now, Q, we're asking how many joules. So that's an X for J, X for joules. 225 is grams, 225 grams. And we go and look at Table B for our heat of fusion of ice, which is 334 joules per gram. Oops, gotta make a correction here. I see a little typo. 255 grams. So heat of fusion, 334 joules per gram. And then at this point, you just plug it and chug it. So X joules equals 255 times 334. The answer in X is going to be some value of joules. Let's see, calculate it up. Simple enough. Other practice problems related to heat of fusion and heat of vaporization. What is the total number of kilojoules of heat needed to change 15 grams of ice to water at 0 degrees? So again, we're going ice to water, so that's HF, heat of fusion. A few videos back, we defined as melting and freezing as that new term fusion, and here we're using it in this equation. Kilojoules is kJ, so we have to divide our final answer of joules by 1,000 to get the right answer. So again, Q equals M times HF is our equation. Total number of kilojoules, Q, equals X joules. We'll calculate it in joules and we'll convert it to kilojoules at the end. M, 15.0 grams. And HF, again, off our Table B, 334 joules per gram. So then we plug it and chug it. X joules equals 15 times 334. Now you're going to have to take that answer and divide by 1,000 to get the kilojoules, because X in this case is going to equal joules. So you're going to divide by 1,000 to get your final answer, which is kilo joules. That's a simplification right there for you. I want to see you do that calculation for homework credit. Now this next one, we use a little scientific notation. So think back to the beginning of the year. 1.0 times 10 to the 5th joules of heat is needed to melt ice at 0 degrees. What was the mass of the sample? So we have Q in this case is 1.0 times 10 to the 5th joules. I'm going to convert that by moving the decimal place easily. It's 5 places to the right. 1.0, 1, 2, 3. I'm going to put 4 more zeros here. 1, 2, 3, 4, 5. That's it. Okay, so 100,000 joules. M equals, what was the mass of the sample? X grams. Okay. And so we know HF is what we need to use because we're talking about melting ice. HF equals 334 joules per gram. So we just plug it and chug it. 100,000 joules equals X grams times 334. Solve for X to get the answer. Simple as that. Algebra, people. These are actually easier because there's fewer terms than QMC delta T. Now, this is referring back to question 1. And question 1 is heat being absorbed or released. So let's think about that. What's the total number of kilojoules heat needed to change 15 grams of ice to water? So if we're going from ice to water, that's a phase transition from solid to liquid. That is absorbing heat. So we have to absorb some heat there. Is this process endothermic or exothermic? The process of absorbing heat is an endothermic process. It absorbs heat. That's a give me. There you go. Heat of vaporization. So we're going to look at the other side of things. So the amount of energy it takes when you are in this portion of the heating and cooling curve. How much energy it takes to take a liquid all the way to a gas. So we're talking about this phase transition here. Now, same identical looking problem. Look at that. Look at this equation. It's almost identical to the one before, except for this one little letter. We've changed an F for a V. Now that value, again, is on table B. And for water, it's actually a very large number. It's 2,260 joules per gram. It takes a lot of energy to boil water. How many kilojoules of energy are required to vaporize 423 grams of water at 100? Remember, kilojoules, so we'll have to divide our final answer by 1,000. So we look for our variables, Q, M, H, V this time. So kilojoules are needed. So we don't know Q, so we're going to X joules. We'll convert to kilojoules at the end. 423 grams. That's our mass. And the vaporization constant for water, 2260 joules per gram. And from here, we just plug and chug. Q equals 423 times 2260 joules per gram. Now, that's why we wanted our answer in kilojoules, because this is going to be a very large number. So answer 1. And to get to kilojoules, we're going to take answer 1, and we're going to divide by 1,000. Equals your answer in kilojoules. That's what we are looking for here. Why do we go kilojoules? Because otherwise we have a lot of zeros in our problem's answer, and we scientists like things simpler. Smaller numbers, scientific notation, proper units. So what's the total number of kilojoules? Again, we're looking at kilojoules, so we're going to have to divide our final answer by 1,000. Completely boil 100 grams of water at 100 degrees Celsius. Again, synonym, boil, vaporization. So we're going to have to use that QMHV. Q is the heat that we're looking for in joules. We'll convert to kilojoules at the end. M is the mass, 100 grams in this case. And HV off table B is 2260 joules per gram. That is a constant value. So we'll set it up. Q equals 100 times 2260. So that equals your first answer, answer 1. And to get your final answer, kilojoules equals answer 1 divided by 1,000. So calculate it. Do it. Do it now. second sample, I think we're going to get to the point where we're going to find the heat of vaporization here. Now, this is talking about of a compound, 25 grams of a compound. So it's not water that we're talking about here. You can't just go to table B and write the number down. And there's some distractors in this problem as well. So we're going to still use QMHV because we're talking about boiling points. And this is how it's going to go. So we find our variables, Q. We're looking for, well, we've got Q, 34,400 joules. 34,400 joules. M, let's see if we have a mass here. Yep, 25.0 grams. And then I think we're looking for HV because it's asking what is the heat of vaporization. That is HV, X, joules per gram. So we set it up just like before, but this time we have our joules. 34,400 equals 25.0 times X. And when you solve for X, you will have the heat of vaporization of this compound. We don't know what the compound necessarily is, but it's going to be a value other than that for water. It's not going to be 2260 when you get to the answer here. Let's see if we got any more calculations we got to go through. Not really, but we have a review of this thing, this machine that's designed to measure changes in heat, and we call it a calorimeter, or a PBOM calorimeter. We're going to do a lab related to this type of thing. We're going to see how much heat is being transferred between objects when you use a calorimeter, because you can measure the temperature change in the water outside of this little chamber inside there. And as you know, if you use the Q equals M times C times delta T, you could figure out the Q variable if we're using water there. So we'll be able to measure the change in temperature. So measure this, and I guess the mass of the object, these two things. The C value is H2O, that's a constant. And so then from there, we can calculate the amount of heat that is involved in a chemical or a physical reaction. And in this type of calorimeter, this machine can actually be used to measure the heat of fusion and vaporization of things if you use it carefully enough. And our purposes will probably just be measuring the change in heat between two temperatures. So there are some heat of fusion and vaporization equations in your practice packet, pages 4 and 5. They are mixed in there, so some of the equations you couldn't do before, you can now. There is a quiz titled Heat and Reactions as well online. So enjoy. Thanks for watching.